Alright, so last time we defined this, we, talked about uh, the pancake problem, which is about, taking essentially strings and then using prefix reversals to get them to their sorted, to the sorted string where you go 1, 2, 3, 4, all the way up to K. And, so the problem here is or let me just delete it. The problem here is if we define f of k to be the the least t such that any t string or no any k string can be sorted in t reversals. And yeah, right. So that's our function. It basically just says, for given any rearrangement of numbers 1 through k, then we can sort it by using at most t reversals.
Yo, let's
Yeah.
squeeze this one up. Let's keep this one in the book. Hey, put it back.
Oh. Well,
Yeah,
then I'm gonna
squeeze
make
this.
it,
Yeah, leave that in the corner.
Yeah,
We're
a
gonna
little
need
reminder for you, Alex. And I think I miswrote.
Yeah,
It.
it's
Oh, who's
in.
that? Hi,
Who's
hi,
that?
Charlie.
Oh, Charlie always joins to
A
interrupt this.
reoccurring appearance. All right. So last time we showed the f of k is at most 2k and at least k minus
K
1.
minus one.
And I mentioned that William H. Gates and Papa Dimitru, they showed some better bounds. Namely, they proved, I believe. Let me just look at it again. Yeah. Okay, so they proved basically a lower bound for 16. Maybe there's a minus 1. Yeah. Yeah, maybe you subtract 1 or something. But the cool thing, or the cooler thing in my opinion, is they showed this.
OCD.
So yeah, 1 second.
What is F, Alex?
What is what?
What is F?
That's the number of T flips that you need. Charlie, it's in the corner.
Yeah.
It's the least amount of flips for
I
a
can't
string
read
of
that shit.
Oh yeah, go ahead and expand it
Yeah.
up.
So
So yeah,
one
if
second. Sorry, Charlie. So we'll move.
No,
Yeah, we'll move this up, and so now to zoom this out a little bit.
ooh,
It's the basically it's just the least t such that for any k string or basically any rearrangement of the numbers 1 through k. So basically like a permutation written as a string. It can
mm-hmm.
be sorted by using at most t prefix reversals. Where basically, so prefix reversal you just missed was, so like if I have 2, 1, 3, 4, then
You swap.
I can look at
You just
these two
reverse.
things and I can
Yeah,
because
okay.
it's a prefix because it's the start of it, then I can reverse it, and that would get us to our sorted string which we want to get to. So yeah,
All right, I got it.
that's exactly what we gotta do. So yeah, before we could get so this funny looking O, a big O of 1 that just means some constant. This asymptotic notation, and it's very useful, or it's very convenient to use that rather than being explicit about constants. Just say, yeah, some constant.
Oh, I see. It's big O
Yeah,
of one, not
yeah. Because
OCD.
basically, the constant shouldn't matter too much. Like what's much more significant is just that the coefficient for this linear term has changed from 1 to 17/16, and from 2 to 5/3.
Both of which are slightly smaller, or smaller and greater in
Yeah. So this
than
is less than 2k, and this is greater than k minus 1. At least when k is big, which is what we care about, because
yeah.
no one is like, I need to know the answer for 100 pancakes. No one really asks this question in general, because math can oftentimes be sort of just a recreational, silly problem.
Kind of like a
But
game.
but people care even less about 100 pancakes than just the computational problem. So, uh, do we actually care about the sides? I guess this part is no longer relevant, and this is no longer relevant. So yeah, this is our end goals. We want to show this, or so. Yeah, I guess this is like a kind of interesting thing. Maybe talk about it some other time, but I'm not gonna talk about it here because the lower bounds is my paper isn't about the lower bounds, so I don't want to talk about lower bounds too much. So let's forget about this, and let's learn a little bit about how this thing is shown. Alright. And I guess
My throat.
yeah. This will make a really great video. I just know. Okay. So yeah, and want to show this. And I'm not gonna actually show it, but I'm gonna sort of tell you how you can show it. So the key idea basically is, or the key thing is, we're gonna define a function phi, called a potential function.
I've heard this word before.
Yeah, I know there's one in calculus.
There is.
And honestly, I don't know enough about calculus to be able to educatedly say whether or not there's a deeper connection there, or something.
I don't even remember what it means. Well, I think I know what it is in calculus, but
Yeah.
I'm not gonna take a shot.
But so essentially, so it's gonna be on our set of k strings, or permutations. So sk, and it's gonna be sent to real numbers that are at least 0. So we're gonna find let's see. Yeah. Okay. So yeah, we're gonna define a function phi from our k strings to positive numbers, and we want a few things. We want phi of the identity string, the sorted string, to be 0. And phi of the string is otherwise greater than 0. So yeah, otherwise. All right. So basically, so like, first off, what this kind of tells us, right, is we want to reach we want to eventually reach 5, 0. Like the sorting is equivalent to now attaining the value 0. And then so the second part, which is useful, is so maybe I should that's kind of property 1 is this rule. And then we've got a second rule, 2, which says the following. Right. So basically, if 5 sigma, so basically if we're not the identity, then there's there's a tau such that basically the potential of tau is less than the potential of sigma. I'm gonna get rid of this now. Sorry, Alex. I know it's really helpful for you. Yeah. And basically, the second thing is that the distance, or essentially the number of reversals that we use to get from sigma to tau, is at most the difference of their potentials. So this is a little bit to take in at first, but so the point is before we do anything really, essentially, so just this I claim that this allows us to deduce an upper bound on f of k. So essentially the point is, so if we start at any point sigma, then until we reach 0, we can always find some tau where the potential decreases, and the number of moves to get there is the most of the difference of the potential. So like essentially, like imagine, you can maybe imagine it kind of like that. I wrote this in my notes, so I'm not sure if this is a terrible analogy. Yeah, but basically it's like we want to reach 0, and so we can always find some place where the potential gets smaller, so we're making progress. And the amount we pay for it, the number of reversals we use, the distance, is at most the difference between these potentials. And so,
how do you get...
And so the claim is, gotta make more space.
Wait, one quick question. How do you get to 0 from that if there always exists a tau such
whenever it's greater than 0, we can get some place where it's less. And so if our potential is like 1 and we only take integer values, then we have to go to 0. But yeah, maybe instead of saying it's on the reals, might make more sense to say it's on the integers.
Yeah, isn't it on the naturals? I thought.
Yeah, you can do that, and that probably makes more sense for what we're doing here. But anyway, so the point is, like, so if I start at sigma 0, then I'll find some tau, that's not the identity. So, when the potential is greater than 0, I can find some new guy where the potential is less, and let P0 be the first potential, and we get a smaller potential, ... until we eventually stop at id k, where the potential is 0. And so, and obviously, if if our potential only takes integer values, and we're always decreasing, then eventually, after finite number of steps, we should be reaching
The identity.
the identity.
Quick
And so the
question.
question is, well, how many reversals do we take to get from sigma 0 to the identity? Well, in the first step, we use at most P0 minus P1 steps, right? Because of rule 2, right? The where this upper bound on the distance, or how many steps you need to pay. Or so maybe I should have this here. So the distance.
Yeah, I'll be back in a minute.
Sure.
Bye.
Sure.
Sorry for
Charlie.
There's always this.
Fuck you.
So the
Question,
distance from
does-
sigma 0 to
Does
k.
tau of 0, like the one that is associated with sigma 0, is that equal to our next sigma?
Yeah. So basically, you choose sigma 0, you get some tau, and then we just write it as sigma 1 because
Okay.
because why use the same letter, different
Yeah.
letters? Because then what would tau be for tau? Yeah, but yeah. So basically, yeah, you apply it with sigma, you get some sigma 1 with less potential until you eventually reach 0. And so if we want to know the distance, the number of reversals we use to get from sigma 0 to the identity, well, so for this first step, we use the most P0 minus P1, right? Because we start with potential 0, we went to potential 1, and the distance to get from here to from this step should be at most P0 minus P1. Does that make sense?
We'll say that makes sense.
You'll say it makes sense? Or maybe it'd be better if I
That
yeah.
I'm guessing those are the same, right? Because it's just the phi of sigma is the same as the potential of sigma.
Yeah.
Or
So yeah, P0 is
yeah.
just so I didn't have to write phi
Yeah.
of sigma 0. Yeah. So this is so that's an upper bound for the number of steps used there, because this doesn't need to be the exact distance. It's just an upper bound on the distance.
Mhm.
Right. And so if we want to know about the second step or whatever, so if the second step, the cost would be at most now P1 minus P2, because you have potential 1 and you go down to potential 2. And you continue ... until you get to, the final potential minus 0.
Mm-hmm.
However,
so you're summing up all the distances between each of our
because if I can take 10 steps to get from 0 to 1, and then I use another 5 to get from 1 to 2, and then let's say 12 to get from 2 to 3, then you can just add up use the steps in sequence to get all the way from 0 to 3.
So wait, well, I guess will all steps or successive, or I guess distance between sigma and tau, will all of those be less than the next? So sigma's the distance between sigma.
It doesn't have to be. So for
Okay.
example, this could be
also
5.
is this the
This could be 10. This could be 2. They don't have to be ordered anyway. But so what's important is how they relate, or that they collapse, essentially.
Okay. Wait. Yeah, sorry. Never mind. I was just confused why you wrote the distance between sigma zero and id k, or the identity of it, but that's because you're doing the summation.
Yeah, it's because I'm
Yeah,
doing the
yeah,
summation. Yeah,
yeah,
yeah.
yeah, yeah, yeah.
It's like kind of like triangle inequality. The distance to get from x to z. Yeah, I'm starting to speak British. X to z. So yeah, the distance to get. So like I'm
Hey,
trying to get
boys.
from you know, uh, Durham to Raleigh. Then I could look at the distance if it takes some number of miles to get from Durham to Chapel Hill and some number of miles to get from Chapel Hill to Raleigh, then obviously I can get to. So it's A miles from Durham to Raleigh
I
and
know.
B
Yeah. So
miles from Raleigh to
the
Chapel
distance
Hill.
from the
I'm
distance.
mixing it up now.
Wait, no. So the distance from x to z will be less than the distance from x to y plus
Plus
the
x
distance
to
from
y to
y to
z.
z.
Yeah, that's
Yeah,
triangle
yeah,
inequality. You know that
yeah,
one.
yeah, yeah, yeah. The classic.
Yeah, yeah. I'm definitely leaving that in the video because I explained this so good. But anyways,
I mean,
okay,
so
so
far, all of this part right here on the corner, this distance thing, I get it. What
yeah,
show?
yeah. Okay, so the important step is this last one, where I say, well, the funny thing is, so here we subtract p1. So here we subtract p1, but here we add p1. So
Wait
they
a
cancel out.
second.
So they cancel
Wait
out,
a
and
minute.
they cancel out, and this cancels
Wait
out,
a
and
wait a
so
minute.
this is equal to just
The
p0
potential of
minus
zero.
0, which equals p0.
Why?
So what this means is that if a guy is potential p0, so if sigma 0 is potential p0, then its distance, the number of moves I need to sort it is at most p0.
That's crazy.
So yeah. I guess I should have, but yeah. So
Where to go?
yeah. So the
That's kind of similar
takeaway
to.
is
Oh, that's just I'm silly. I was just don't worry about it.
sure. Uh, takeaway f of k
Is going to be less than or equal to
equal
p
to
zero.
max. Yeah, if we max sigma of the max. So yeah, if we take some potential function and we look at all the strings, uh, if the potential is always less than something, then f should be at most that.
I see.
Yeah.
Yeah. So we take the worst string of length k, the max the first potential
Yeah.
of that string. Yeah.
Yeah. And so I probably should have mentioned this earlier, but there's a nice number file video on so like about potential functions. There's a number file video you could check out, which also talks about this probably more eloquently and
This sounds kind of similar.
accurately than me. So like I believe so like potential functions appear in something called uh,
Calculus.
Conway's soldier problem. Yeah, I should have set this up start. Um, and
Oh yeah, just add an annotation.
yeah,
Real ones remember.
see Conway checkers. The video Conway checkers on N file 2. Yeah, so it's the second number file channel, and they have a nice video about potential functions and a neat problem. I didn't really understand it the first time I saw it, but now I do because several years have passed. Yeah. Okay. So that's yeah. Kind of the point is that that's our strategy now. We want to define a potential function where we know the maximum is we want the maximum every string to have potential at most 5/3 k plus some constant. Plus some constant.
Yeah.
And so, but before I do that. I'm going to talk a bit more about these potential functions. Because there's actually a funny thing happening. Or actually, maybe I shouldn't get rid of these rules so fast. Because maybe they're useful to still consult.
Yeah, just quickly squeeze these down.
No. I'll get rid of the takeaway for now. But so... There's actually one potential function which is really good, or it's really accurate. If you just take 5 sigma equal to the minimum number of moves to get from sigma to id k. Obviously. So basically, obviously, if sigma is not the identity, so if sigma is the identity, then you don't need any moves to get to id k, right? It's already sorted. Yeah. And if it's not the identity, you need at least one move. So the first condition, yeah, that works. And for the second condition, it's not as obvious, but it's also true. Essentially by like pretty much triangle inequality or whatever. Essentially, if I have id k and I have some point which is two moves away from id k, well then obviously there must exist then there must be some path of length 3 from the identity to sigma. And so I could just take tau to be another guy in this path, and the distance will be, and so that's essentially how you see it. So really, there exists a potential function where where f of k is exactly the maximum of the phi, and so you're wondering why. Great, let's just take phi to be this. But the problem is, we wouldn't know how to take the maximum of this. We did immediately, the question of what is max sigma of d sigma in k. So yeah, the question of this is exactly our problem, and so. Yeah, rewriting in this form does us no good at all. And instead, what we want is some stupider strategy, where we aren't perhaps making the smartest moves, but we're doing some heuristics that basically that we can analyze. So this is a very common theme in math, where basically.
Question for everyone who's watching, just for the uninformed, and I know what this means, so I'm not too worried, but this is just for everyone. What does heuristics mean?
So, a heuristic is like a rule of thumb, yeah.
I see.
And is it spelled E-U or U-E? I bet it has to be E.
I think it is that.
Yeah, because otherwise it'd be heuristic, and
which is silly.
Silly, yeah. Heuristic, rule of thumb, rule of
you
thumb.
Nice.
Yeah. So, but a general rule of thumb in math is oftentimes to prove things you use dumb strategies
To come up with the smartest strategy.
that are easy um, to analyze. So like basically the problem of doing the exact optimal shortest path from like sorting a string, it's like actually shown to be like NP complete, and so it's like it's an impossible problem. But like instead of doing the exact smartest thing, where we don't know how to do that at all. If we instead we come up with some stupid algorithm which we know how to analyze, then like basically yeah, when you sort of simplify, basically like a permutation has a lot of information in it, right? Like so this sigma has k different things going in on it, and uh that's a lot of stuff to that could influence what's the smartest decision to make at a certain time. But if instead what we make our decision based off of like four things happening in sigma, then it's a lot more tractable, or it's manageable to sort of to know what's happening, or to break down the cases of what could possibly happen, and that's basically what we want to do. Uh, so yeah, like a good, I guess I have a bullet on this. Yeah. Like another way to think about it is maybe like it's like kind of a discrete gradient descent or something. So gradient descent is kind of a thing from machine learning or whatever, where say you've got some kind of bumpy function or something, and you want to find a low point in the function. And so if you start here, then the lowest point of the function, say, is right there, but to find that spot, you'd have to look at a huge amount of the function and be able to say, oh, that's where it ought to go. So, but if you just looked locally, you'd be, what you kind of see is, hey, it seems like I'm kind of on a hill, or the slope is going downwards in this direction. I should probably take a step there. And so if you basically, you'd find a local minimum over at this point.
Mm-hmm.
And so basically, like, this local approach isn't optimal, but it does a decent job, and it only uses a little bit of information. It just says what's basically the derivative at the point I'm at, rather than what does the entire function look like, because there's a billion different functions, and you'd have to do something for every single function. With a simple strategy, I'm always gonna just go down my slope. It's super simple.
But you got to go down all of the slopes then.
Yeah, well, so basically to reach the bottom of the potential function, or to reach the zero in a potential function, you eventually do have to get from some local minima kind of to there. So maybe instead of this being in 2 dimensions, it's like in 3 dimensions or something. And maybe think about it as traveling through the woods, where perhaps you don't take if you're trying to get from A to B, right? Perhaps you don't take the shortest route. Perhaps your like trail meanders a little bit, but you're always kind of like taking steps in the right direction, and you're like following obvious trails, and like you're doing stuff which, cause if you don't know exactly where B is, like if there isn't a landmark and it isn't your GPS, then you gotta be doing something crazy to just know, hey, I gotta go straight in this direction to reach B. But if you're like, I don't know, exploring kind of according to some landmarks and some advice, maybe you can kind of get there pretty efficiently and in a way which sort of doesn't require fucking
Um,
magic
omnipotent.
insight to the problem.
Yeah.
Yeah, I don't know how nonsensical these kind of hand wavy metaphors uh sound. I
Don't
actually kind
worry.
of do sound
I
like
get it.
nonsense.
No. I get it.
Yeah, but so that's kind of what the potential function we want is something that basically or that's kind of how the potential function works, and here's the specific criteria we want. Good potential function or or I guess basically we need two things. Well, so first off, we gotta need to compute uh an upper bound at least for the max. So like basically it needs to be like the function needs to be determined by something where this
Oh,
maximum is like where we can say anything about it. And then so like that's basically so that we can get a good bound on F or be able to get a bound on F. The other thing is we need to be able to make local progress. And so actually the kind of diagram I showed before, like this whole sign thing,
mm-hmm.
yeah. So here the strategy, like a strategy where you just go towards the bottom point, like you go towards a dip. That probably might be bad because once we get stuck the dip, there isn't a way to make local progress, and you need to define your function some way such that somehow you get from here to there. And like
Check it out. I've got a plan for this. You draw a line from that point, and then you've got a new function, and then you go from there.
yeah.
But
Yeah, well, that's kind of a nonsense diagram, which doesn't fully reflect the problem.
yeah, can't
So
really do
unfortunately,
anything with that.
your brilliant solution is not applicable. But so these are two criteria. Would it be useful to put them at the bottom? We'll just we'll keep this in our memory
Yeah, we
for
need
later
this.
use.
What do so?
Or
Hold
what if we
on.
put it at
It
10% of pass?
isn't 10 or isn't the distance between the phi of or phi of sigma uh or sorry, yeah, the distance of phi of sigma and the identity of k, isn't that the same as the max of phi of sigma?
Um, sorry, could you run that by me again? So, So the distance from sigma to the identity.
Yeah,
Yeah, so this will be at most phi of sigma.
I see.
Yeah, but it can be more because we're gonna be doing some silly strategy, which is stupid, but we're gonna be able to say something about this maximum. Like we're gonna make simplifying assumptions such that we can say something about the maximum overall sigma of this phi, and so that we can make local progress, whatever that means. So specifically, what we're kind of gonna do is this. So given some sigma, which is gonna be some sequence of numbers, right? So it could be 3, 2, 1, 7, 5, 6, 8, 9.
You're
Let's
missing a
see.
number. You're missing a number.
Oh,
4.
4. My bad. Yeah. So basically, what Bill Gates did, is he sort of Well, so we want to be able to make local okay. So what they define is they said that a block in this string is a group of numbers which are consecutive or reverse consecutive. So like 3, 2, 1, they're like decreasing, right? But only by
Yeah.
1. And so 7 forms its own block. You can't it doesn't differ from 1 and doesn't differ by 5 by 1. So this is a block. This is a block. This is a block. And so we can give it any permutation. We can decompose it into blocks, and some of these have size 1, and some of these are larger. And so what they do is they define phi of sigma to be equal to, I think it's 5/3 of the number of blocks, or so they first off define S of sigma to be the number of singletons, essentially. Number of blocks.
Of size 1?
Yeah, of size 1. And then, the big blocks is number of blocks.
Not size 1.
Yeah, of size greater than 1.
Wait, but can't S of sigma be equal to the length of sigma?
Yeah, it definitely can be. And that's what happens when there's no adjacencies, essentially.
Yeah.
So, like the example we gave before, this has no...
Yeah.
Though, so actually a technical detail is they say differing by 1 modulo k. So actually they'd say 1 and 4 would form a block because, if you imagine this on a clock, right? 1 and 4.
Yeah.
But so modulo 4, 1 and 4 are differed by 1. So instead you need something like 1, 5. No, fuck. You need a 1, 4. Oh, okay. No, I know the fix. But so if we added a 5 now, then this is no longer. Yeah, then there's everything is a singleton, because there would be no blocks. There'd just be singletons. So we define the singleton count and the big block count, And so the potential function they find is just gonna be linear in these. So we're gonna have it's 5/3 basically the number of singletons plus, and they might have actually described it a little bit differently, but it's, oh yeah, they don't even, they do something in my opinion which was silly, which they say they apply it to the duality theorem of von Neumann and stuff, but you can just define a potential function, and I think let me, yeah, give me a second.
Wait, is it the difference between any two modulo k if that is equal to 1 is what you said? Sorry, I was just so like doesn't matter. It doesn't matter. It's an added detail. I was just unsure, and I don't really know why. But
yeah, 1 second. So plus b sigma. Yeah, I think this is correct. Yeah, and they basically define sigma, I believe, to be this, where it's 5/3 number of singletons plus a number of big blocks. And so what was your question asked? Do you want to say it now?
yeah, wait, what was the thing with the modulo k?
Yeah, so here, if we have 4 letters, then 1 and 4 differ by 1 mod 4. Uh, and so they'd be considered a block.
I see.
Yeah, yeah, but once you have the 5, then they're no longer considered a block, and this is all singletons. And so, basically, they work with this, and they start with this potential function, basically, and it's actually kind of not quite a potential function. Essentially, this function gets minimized once we have a single block, right? So basically, but like the same kind of argument applies that essentially, if we have something with potential function p, then we can reach something that's a single block by only using at most p steps. And then separately, or so yeah, I should start a new thing, or I should
No, no, no.
yeah, so maybe even, yeah, bye potential function.
Bye.
Yeah, so very small we'll have what, S sigma, B sigma, R, and then yeah, this is the kind of phi they're using. I might be stating it wrong. I don't think I am, but maybe I am.
As in saying it wrong, as in phi versus phi, or saying the function wrong?
Yeah, the function might, like, the constants might be different because they don't use constants, but I think this is the right constant. But I won't be doing the calculations, so it shouldn't matter. But essentially, so here note that the thing doesn't get minimized at 0. So this isn't quite the function I was talking about, right? It doesn't attain 0 because, like, if you have a sort of thing, it has just one block, and so that's 1.
Well,
But essentially, phi, okay, so I'm gonna switch back to black. Phi of a sigma minimized when the B sigma equals 1. And so basically by the same logic as before, essentially, we'll know that if some sigma has potential P, then the distance from sigma to some tau is at most P, where tau has one block, essentially.
Wouldn't it be?
Yeah, and I guess the
You mind
singleton should be 0. So
Wait, what doesn't that mean? The distance is. Oh, never mind, never mind.
yeah, or you could even say the distance is at most P
Oh,
minus 1.
yeah,
And
that's what I was.
but yeah, so basically this tells us, so if we get some upper bound of the potential function, it'll tell us we can reach a single block, no singleton guy in P steps. And then basically then in their paper they also show that for any tau that looks like this, right, where we only have one block and there's no singletons, then the distance from tau to the identity is at most 4. And so bada bing bada boom, maybe we call this cool phi, uppercase phi. And so this should imply an upper bound of the form f of k is at most the max over the sigma of now our uppercase phi of sigma, like +4 or whatever. And this +4 we just write as plus big O of 1, because who cares about the actual constants, right? And so we're almost done, ish. So in the next part, right, I'm gonna be covering a little bit of how, because right now we haven't proven anything. We haven't said this is a potential function in the sense that we can always decrease the potential when it's greater than the minimum. But it's true, and we'll talk about this more, about how you make these local improvements. But for now, I'll show how this implies what we want, or namely, if you remember this thing over here, right?
Oh yeah, could you expand that for a sec?
Yeah. So, oops.
Yeah. The classic.
Yeah, we want to show that f of k is at most 5/3 k, 5/3, as you can see. K plus big O of 1.
Well, it seems that because like there's at max, there can never be more than k singletons, right?
Yeah, there can be at most k singletons, and there can be at most k blocks. So yeah, it's pretty obvious. But I'll spell it out after cleaning this up. Or let me what did I do? Oh god. Wait. Oh, I didn't do much. I thought it really. I thought I'd really screwed something up, but really it was like that to begin with. So, recall that, yeah, so, yeah, big phi of sigma is just equal to 5/3 the singletons in sigma plus the big blocks in sigma. Well, obviously, the number of blocks, big blocks in sigma, plus the number of singletons in sigma
is equal to the length.
Is the most k, because
Yeah.
every index either belongs to a singleton or a big block. You can even say more. You can say that this holds true
Can I?
because each
Yeah,
block
because
contains at least two of these
yeah,
indices or
and
two of our
so it removed
letters,
two
right?
singletons. Yeah.
And so, well, obviously, um, so it's whenever we an index belongs to a singleton, this thing increases by 5/3, while if we create a new big block, it only increases by 1. So we should assume all the singletons, right? It's just kind of obvious, right, that you could use some algebra, I'm sure, to confirm this for sure, but it just kind of seems obvious that essentially, right, the uh um
Go ahead.
that basically then this should imply that phi of sigma is at most 5/3 k.
Okay. Yeah.
So yeah, do you agree? Because this is at most k, and yeah. So let's get rid of this, and so yeah. So this is at most k, and now we multiply by 5/3, right? To both of these, and now this is
Yeah.
at most 5/3 k. Now, this is equal to our thing, right? Except we've added 2/3 this, and therefore, we get. So now we get, because this term is positive, that obviously it should be at most 5/3 k, because phi of sigma is at most 5/3 k minus this positive 2/3 b sigma thing. I'm overcomplicating this. It's just kind of obvious that
Yeah.
that this is true. And so, like I said just a moment ago, our distance of sigma to id k by something they prove, and it's really short. It's just kind of these two diagrams give exactly what you wanted to show. Uh, maybe I'll explain that. I don't think I will, but this is the most this weird potential plus 4, and so we've got the thing we wanted to show, and so since holds true for all sigma, we know that f of k is almost the 5/3 k plus 4, which is big O of 1, because it's just some constant. Yay! We're happy. And yeah, hopefully that was kind of clear. Is anything confusing? And do you want to see this diagram explained a little?
Zoom in. I have poor vision.
Yeah. But then, Alex, how have you been reading my stuff in the corner?
Oh, I just get really close. I really can't read from that far away anymore. It's kind of fogged. Although I am sitting back in my chair. Let me see.
Yeah.
Is this? I noticed with a lot of these like sorting sort of problems, which I guess you can call it that,
Yeah.
or sort of rearrangements. They use a lot of modulo, like considering modulo groups.
Yeah. So I mean, here the thing is that so working otherwise, I guess we'll see more when we talk about kind of how it works next thing. But the thing is, if things aren't symmetric, then like what happens is that if I'm in a state where how they make local improvements roughly is, so we'll start at we assume sigma starts like some letter I, and then maybe it's part of a block, and so we have I plus 1 or I minus 1 maybe, dot dot dot, and then to some j. And so if I is equal to, so if I was 1, let's say, right?
Yeah.
So if our pressure starts 1, 2, 3 to, I don't know, maybe 8 or something. And
Mhm.
so what the strategy wants us to do is it wants to make a bigger block, or it wants to find some singleton or something. It
Or,
either wants to find some other block and combine it. So like
yeah,
find I
like J.
minus 1, I minus 2, and say, oh, I can, if I reverse this whole section, right,
Mhm.
then these guys will combine into one single block, and that will decrease our potential. And
Oh, yeah, and then you
and
flip it
the same
again, and
if
they
this is a
say,
singleton, then yeah, we've the big number of big blocks doesn't change, but the singletons decrease, and again the potential goes down. But so the problem is if I is equal to 1, and I don't allow for modulo stuff. So let's say, I don't know, k is equal to 20, and so 20 is here. If I'm not allowed to reverse this to decrease the potential, I'd have to waste some moves to do something else to try to decrease the potential. And so, but by like adding this sort of symmetry, so that we can always decrease the potential, when one of these weird edge values is at the front,
mhm.
really makes things a lot easier. And it doesn't really matter, as they show this little diagram. This diagram says, oh, by using most four moves, that we can maybe we waste 4 extra moves, but otherwise it suffices to consider doing this cyclic thing where we can work mod n or mod k, and that just greatly helps because so reduces from sorting to blah 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 to basically this to now doing I to k and then 1. So this is at least a bit easier than that, and the difference is 4 moves, and so yeah, it doesn't really matter, and so we consider the easier problem.